All right, here's the one that went poorly in class when I sat down with a calculator and used bigger molar masses, meaning more decimal places. Everything worked out fine. So I figured I'd record it, and that way you have at least one more example of empirical formula. All right, so if I look at this and I read the question, I see that I do not have percentages that add all the way to 100. That is okay because it says the rest is oxygen. So I can take the fact that all of my parts should add up to 100%. I can subtract from that whole the parts that I do have, so the 50.84 and the 8.53. And I can figure out the part that should be attributed to oxygen, which is 40.63. Whoops, that should be a percent. Now that's step one. Step two is to figure out something in terms of mass, because we're not going to work with these percentages. We need to work with something that we can compare. We can get to something we can compare by using mass. So what we're going to do is assume that we have a 100-gram sample. And if we have a 100-gram sample, that allows us to go straight from percentage to grams, because all we're doing is taking a part out of the same size whole. 100% and 100 grams, those have the same size. If I took 50.84% of 100 grams, it would happen to be 50.84 grams. So this assumption saves us a lot of time in figuring out math. So I'm going to go ahead, I'm going to write down all my masses. Two of which were given and one of which I had to figure out. Now, I cannot compare these numbers because these are all in grams, and they're grams of three different things. I have three different atoms there. So since they each have a different mass, comparing the grams of them is completely irrelevant. It just doesn't matter at all. So I'm going to take all of them and divide them by their respective molar mass. So notice that as I do this, I'm writing down both the unit and what the unit is trying to describe. So I have something about the individual element in here. That's going to help me keep from getting confused when I move from one part of the calculation to the other. I'll be able to tell which one I'm talking about. So if I do these quick little arithmetic steps, I end up with 4.23 moles of carbon, 8.46 moles of hydrogen, and 2.53 moles of oxygen. Now, these are not numbers that can go in a chemical formula because they represent fractions of atoms right now, right? So we can't, these guys are whole because my mole ratios here are in terms of whole atoms. Here I'd have weird decimal places. We don't do that. So what we need to do is try to get them towards a whole number. We do that by taking all of these. Remember that this is one large mathematical operation. Take all of these and divide by the smallest. What this does is ensure that we have at least one whole number, because anything divided by itself is going to be 1. So at the end of the day, I'll have 1 mole of oxygen, 3.34 moles of hydrogen, and 1.67 moles of carbon. Okay. These numbers over here are the result of taking these numbers and dividing it by the smallest one. Now, I'm still not in a point where I can write a chemical formula because my chemical formulas are whole numbers. But I can look at the 1.67 and see that it's really 1 2/3. I can look at this guy and see that it's really 1 1/3. These are pretty common fractions, and we can get rid of this number in the denominator if we take all of these and we multiply it by some whole number. So we're going to take 3, multiply it by 1.67. We're going to take 3 and multiply it by 3.34. And we're going to take 3 and multiply it by oxygen. Because, again, one big mathematical operation. Doesn't matter that oxygen doesn't have decimal places there. What I do to one part, I'm going to have to do to all the other parts. So 1.67 times 3 is 5. So I should have 5 moles of carbon. 3 1/3 times 3 is 10, so I should have 10 moles of hydrogen. And 1 times 3 is just going to be 3, so there's 3 moles of oxygen. So if I put these guys in a chemical formula, it will look like this. All right, now let's take this one step forward, okay? And this is not given in this problem. This is a new problem. Let's say that I know the molar mass of the molecular formula is 236.26. Now, if it is in a molecular formula question, I will have to give you this value. So let's assume that this is some new question. I have given you this value. This has to be given to you in the problem. I can move from my empirical formula that's here in the red box to whatever the molecular formula is by comparing this molar mass to the molar mass associated with C5H10O3. So what that means is I'm trying to move from this atom count here to the actual atom count, and the thing that I have to compare to one another is going to be the molar mass. So figure out what 12 carbons, 10 hydrogens, and 3 oxygens would weigh, which is about 118.13. Okay, this is the molar mass, the 118 is, of the empirical formula. I know that the molecular formula has a mass of 336.26. So what I'm going to do, and I'm going to do it in this way in hopes of getting a whole number, is put the big number on the top. So this is the molar mass of the molecular formula. I'm going to include the unit, but you don't have to because it's the same in both places. It cancels out anyway. And then I'm going to put that molar mass of the molecular formula over the molar mass of the empirical formula. Now again, those units are going to cancel, so they didn't really need to be included. And then when I take 236 and I divide it by 118, I get 2. Now again, this number here should be really darn close to a whole number. If it's 2 fractiony, your empirical formula is probably wrong. What this 2 tells me is that my molecular formula is 2 times as big as my empirical formula. So I essentially need to take this and multiply it by 2. And when I say multiply it by 2, I mean the subscripts. So my molecular formula is going to be C10H20O6. If you want to double check yourself, figure out what the molar mass of this is. It really should equal that.